Professor Ferrara received her PhD in computer science and electronics from the University of Genoa. And for 6 years, she was a professor in the Department of Communication, Computer and System Science of the University of Genoa. Since 1998, she started her career at the University of Pavia, and currently she's a professor at the Department of Electrical, Computer and Biomedical Engineering of this university. Professor Ferrara is well known for her contribution in the development of the concept of a sliding mode control, and her research activities are mainly in the area of advanced automatic control of convex systems, with applications to mechanical systems, robotics, automotive control, power system control, process control, and vehicular traffic control. She has had several editorial activities. Currently, she is the senior editor of the IEEE Control System magazine, the subject editor of the International Journal of Robust and Nonlinear Control, and the associated editor of Automatica. She is now one of the experts appointed by the Italian Ministry of Research to issue the National Research Plan for the research area Sustainable Mobility. In this lecture, she will talk about the application of connected and autonomous vehicles to control and optimize the traffic condition on freeways. So, Dr. Ferrara, there is a recent controversial question about whether the CAVs could play a role in sustainable mobility. I would like to ask about your opinion on that.
Well, I think that the role is an important role, the role that which can be played. And well, I think that in my talk you can have also an answer to this question. I think that I will try to clarify in which way. Control is an important, let's say, part of the good functioning of a system. Optimization is an important ingredient. What I'm going to tell in my lecture, in this talk, is how to mix the two components, so how to design optimization-based control algorithms in order to improve, let's say, the quality of the evolution of traffic systems. And in particular, I will show how, for instance, to reduce the fuel consumption. I will show you how to alleviate the congestion problems you may have in traffic system. And this, of course, may have an impact on climate, for instance, and on the environment, also on the, let's say, life of people and the quality of life of people. So sustainability is an important aspect which is definitely tackled by what we are going to see in this lecture.
Perfect, thank you. So we're eager to hear more from you.
Thank you so much, Kimia.
Yeah.
And thank you so much to Kimia and Zhao and all the people who assisted me during the preparation to this lecture. And also thank you so much to the organizers. It was really a nice effort in these difficult times to maintain this tradition, to have this kind of schools, summer schools. It's important for students, but it's important also for us, let's say also for professor and teacher to be involved in spite of the difficulties of the time. So, Kimia, if you consider that it is doable, I will share my screen.
Sure, of course.
Okay, and I will start this lecture. As the other lectures that you have already attended in the school, this lecture is subdivided in two parts. You see, the title is Optimization-based freeway traffic control via connected and automated or autonomous, if you prefer to use this different attribute, vehicles, the so-called CAVs. I would use this term, which is quite standard right now. But in order to introduce this main topic, which will be mainly discussed in the second part, I've decided to start going back to some elements of traffic control, illustrating what is the role or what the role of control may be in traffic system. And I will present some approaches, some algorithms that have been developed by my groups. When I say my group, I think of my PhD students, my postdocs, my collaborators, not only students, they are also colleagues from different universities in the last, more or less in the last decade. So I will start from that, from that part. And then I will move to the use of connected and automated vehicles. In the first part of the lecture, so you will see something which is in some sense rather classical, but I've done my best, and I hope to have succeeded in this, to select topics in thinking of my research papers, which should be different, I believe, with respect to what was already presented by my colleagues. I'm thinking of Professor Marcos Papageorgiou, I'm thinking of Professor Barde Scooter, I'm thinking of Professor Kalle Johansson. So we are colleagues, we know the work of each of us very well. I will present also some paper co-authored by some of the people that I've just mentioned. And so I've done my best to select topics that are different. Of course, it may happen that some overlapping occurs. In that case, consider what the Latin people used to say. So repetita iuvant. Repetita iuvant means things repeated can be beneficial in Latin. And so in case there is some overlapping, please accept that and wait for something new in what I will say later. Okay, so I start with a few words of introduction. Let me see if I can move on with the slide. Just a few words of motivation. So I will give you a very brief introduction, then I will tell you something about classical control of traffic control with some, let's say, originality element, let me say like that. And then I will move to the more innovative part, those related to connected and automated vehicle. So you know that in road traffic networks, it is really crucial to be able to have a good, let's say, management of the network itself, and this in order to solve all the congestion and the pollution and other kind of, let's say, problem which can be related to this kind of systems, which we face any day of our life, at least if you live in a major town. The picture that you see here was taken by my daughter, Camilla. Camilla is a student in Milano, so she moves from Pavia, the town, sorry for my dog. I hope that someone in the family is arriving. So my daughter is studying in Milano, and she has to travel any day. And this is the situation that she has to face anytime she goes to attend lectures in her university. So this is 7:25 in the morning in Milano. So it's something very common. And well, another aspect related to traffic is the fact that traffic congestion has an impact not only on pollution, not only on the climate, but it has a very strong impact in terms of road fatalities. And consider, for instance, that the roads in the European Union are considered among the safer in the world, but in spite of that, any year we have 25,000 people losing their lives on the roads. And well, this is a strong impact that we have, the so-called direct fatalities, but we have also the so-called indirect fatalities. As I said, the indirect fatalities are those related to the air pollution. And if you look at this picture that I've just taken from the World Health Organization webpage, you can see that transportation systems are considered the second source of fatalities in our, let's say, industrialized world. So we have to do something. We have a mission, also in considering that, in particular, thinking of people as I am, so control expert, we have the possibility of making an action, having some impact on the system. And so we have this mission to try to solve the problems or alleviate the problems that I've just mentioned. Traffic control is a kind of particular control system, which can be anyway recast into this classical scheme that you see in the slide, the so-called closed loop control system. So we have the road traffic system, which can be seen as the process to control, upon which some exogenous signal, say, have an impact on them. So the exogenous signals are kind of external inputs which are not manipulable. And then on the system, we have actuators, which are devices which allows us to have an action on the system, exert an action on the system. And then we have sensors, which are devices which allows us to measure some quantities. In case, for instance, the quantity that we are able to measure is for instance, the density of traffic, we can assume to have some reference density. So the density which, according to some, let's say, prescription, are the prescribed density for any particular point of the traffic system. And then we can compute an error, and we can design a controller such that using the error as input, we can exert the action, the correct action on the system. Let's say, traffic control, the objectives which are typically used, maybe several. I've just mentioned some that I will use during the talk. For instance, the total time spent by the vehicles in the road traffic networks, the maximization of the total traveled distance by vehicles in the road traffic networks. Another possibility is to maximize the so-called capacity exploitation of the system. So, for instance, selecting some specific set points in order to make the system, let's say, be exploited at the maximum of its possibility. Okay, as I said before, we started just making some comments about sustainability. And well, of course, you can also have some control objectives which are strictly related to sustainability. And sustainability is something which is related to emissions, to safety, to noise pollution. So we may want to reduce the noise. Of course, there is the aspect related to energy. So energy efficiency is another important aspect, and also the environmental risk mitigation. Things of freight transportation, when some dangerous kind of good is transported. So we can also decide to formulate a control problem, and optimization-based control problem in particular, in order to minimize the risk, the environmental risk, and so forth, and so on and so forth. So these are just examples. And the idea, which is, let's say, the basis upon which the second part of the talk is built, is that related to the possible future scenarios that we may have in traffic systems. I'm particularly thinking of freeway traffic system, but consider that what I'm going to tell you may be valid with some, let's say, slight variations also for urban scenarios. So what is different, or what is becoming more and more different, thinking also of the future years, is the fact that instead of having in our traffic system only human-driven vehicles or low automation vehicles, traditional vehicles, we will have more and more the presence of highly automated vehicles, not necessarily autonomous vehicle, but this is why I prefer to use the word automated, because let me say that if the vehicles are autonomous, they can be even more efficient in terms of control or controllability of the traffic system. But if they are anyway highly automated, and when I think of highly automated, I'm just mentioning vehicles with on board some adaptive cruise control systems, some braking and traction control algorithms. So something which is already in the market, something which is already, let's say, considered feasible or already produced in some cases. And well, having this kind of vehicles, we can think of controlling the traffic system in a way which is completely different with respect to what has been done in the past, and I will clarify this in a moment, by creating in particular this kind of artificial moving bottlenecks that I've indicated in the picture. I don't know if you can see this kind of platoon here. So the idea is to create moving actuators instead of having some infrastructure-based actuators, which can exert actually an impact on the traffic. For instance, simply slowing down the traffic, but this can have an effect in terms of congestion mitigation. I will be more specific. So this is just the introduction, and I want to go immediately to the more technical part. So as I anticipated to you, the lecture is divided into parts. The first part, then I will make a break in the middle if you think it's fine. In the first part, I will present a rather brief, let's say, review of a rather classical method. I say rather classical for the reason I said before. They are based on classical idea, but they are anyway rather original. And then I will discuss the new methods, those based in particular on connected and automated vehicle. In particular, I will present also some particular models which are used to incorporate the presence of connected and automated vehicles in the traffic system, which is something rather new in the literature. And I will show you how to use these particular vehicles to control the macroscopic traffic. So we will see a kind of macro, so macro, let's say, or multi-scale approach. Okay, so let's start from the classical methods and say a few words about in particular, the models, first of all, to be used, and some methods for controlling the system. When we design a control system for traffic systems, we have to follow the same, let's say, procedure that we are familiar with. So I believe that the majority of you have a certain background in control, but the idea is anyway that a control system in a classical, let's say, way to think of this concept is designed on the basis of a model of the process. So it's the so-called, what is normally used is the so-called model-based approach. And this is the classical, very classical approach also in traffic control. So there is the need to formulate a model of the system. Considering traffic system, the classical models go to describe the traffic flow in the system, and they can be of different type. So typically we have a microscopic model, we have mesoscopic model, and we have macroscopic model. Consider that the microscopic model are models which describe the single vehicle as if a single vehicle were a kind of agent moving in the network. Mesoscopic model are a kind of intermediate scale model. So the vehicles are still present, but also car following effects and the line changing effects are depicted. And macroscopic models are those typically used or majorly used for traffic control design, especially in freeway. And in my talk, I will, let's say, keep the focus on freeway systems because, to be honest, are the kind of traffic system I've devoted my research in the last decades. But anyway, this kind of model, macroscopic model, can be also extended to other kind of traffic system, like even urban. Why not? When you have any kind of models I mentioned before, so micro, meso, or macroscopic, you may have continuous or discrete model. And in case you have continuous or discrete, in both cases, you may have first order or second order model, which are the typical model. First order only describe, typically thinking of macroscopic model, the density evolution. Second order model typically describe density and velocity dynamics, so the dynamics of both the density and the velocity of the macroscopic flow. And then very often we may find single class models or multi-class model. When I say multi-class, I mean models in which different types of vehicles, like for instance, cars and trucks, or let's say, for instance, let's say kind of vehicles like bikes or different kind of vehicles, or buses, for instance, are distinguished by the classical cars. And just to give you a very brief review of the classical models, I mentioned a model that I believe also some of my colleagues have already mentioned, which is the well-known Lighthill, Witham, and Richards model. This is a model which is, as you see in the slide, described by this differential equation. It's a PDE, actually, it's a partial differential equation, and which is based on the density, and this of rho is the density of the traffic flow, t is time, x is space, so it's a kind of, let's say, conservation equation, to call it with its name, and it is based on this function f, which is the so-called traffic fundamental diagram, so a diagram describing the so-called theoretical relationship between the flow and the density of the macroscopic traffic in a steady state conditions. This model was introduced in the 50s of the last century, so we are talking of a very classical, very ancient in some sense, at least from your perspective of young students model. This model was anyway the basis upon which the other models have been developed. For instance, the very well-known cell transmission model, the so-called CTM model, it's a model which is a kind of discretization of the model we have seen before. And the discretization is performed both in space, subdividing the freeway into a collection of cells. And it's, of course, it's also performed in time, with respect to time. As you see, for any cell in which you can subdivide the freeway stretch you're dealing with, we have a first order equation which describes the evolution of the density in the cell. So rho with I is the density inside cell number I. And here you see that we have a flow entering the cell and a flow exiting. And in particular, if you look at the flow entering a cell, you can determine this flow simply on the basis of a very classical demand and supply mechanism. A mechanism which is very easy to explain. So you have a certain volume of vehicles which ask to enter cell number I, but cell number I has already a certain number of vehicles inside the cell. There is a density which characterizes this quantity. And of course, the capability of cell I to accommodate entering vehicle has to be considered. So the supply of the vehicle is exactly this capability of accepting new traffic entering the cell. So if you consider the demand of vehicle which asks to enter and the supply, so the capability of the cell number I to accept the new vehicles, you can compute the minimum and get the accepted input flow in any cell. This is a very simple idea. The CTM, so the cell transmission model, was originally described for a single stretch, so a kind of a tube, so a kind of linear piece of road. But then there was another paper, still written by the author of the CTM, D'Aganzo, in which also some new cells were introduced, the so-called merge and diverge cells, which are the bricks on the basis of which you can build an entire traffic network and then model something which is a real-world traffic system of very close, of course it's a model, so it's an approximation, but it can be a good model of a traffic system. Of course, there are slight differences, and one of the problems, one of the issues which one has to consider when using the CTM is the let's say difficulty of this model, or the impossibility to be very precise of this model to describe an effect which is present in real traffic, which is the capacity drop effect. This is an effect which occurs when you have a congested cell, when you have a bottleneck, so a congestion. If you look at the flow exiting that cell, the so-called discharge flow, this is typically lower than expected, so lower than the capacity of the bottleneck. And this flow reduction, which is observable in real systems, is typically around the 5 up to the 20%. So it's not negligible, to be precise. Unfortunately, the classical CTM model cannot describe this effect. There are many variations to the basic CTM models, which are proposed just in order to accommodate or to describe the capacity drop effect. And one of these variations is, for instance, presented in the paper that I just indicated for your convenience at the bottom of this slide, which was a paper, as you see, co-authored with Professor Papageorgiou, and is also co-authored with my colleagues, with the colleagues of Professor Papageorgiou, also very well-known name in traffic control, Ioannis Papamikael, and my PhD student, former PhD student actually now, Giulia Piacentini. Well, this is something that I will use again in the second part of the lecture. This is why I mentioned this paper. Another model which can be useful, and it's rather convenient in terms of control design for its simplicity. It's a model that I proposed together with Professor Canudas de Witt, which is called a variable length cell transmission model. It's a model which is very simple in the sense that it is based on free differential equation only for a certain freeway stretch. And the free model, the free equation just describes the density in the two parts in which the freeway stretch considered is, So for instance, we assume that there is a congested part and a free part, a non-congested part. And so we have the density describing those two parts. And then we have the evolution of the length of the Q, which represent, or the shock wave, if you prefer to use a more technical term, which represent the evolution of the congested part of the cell. So if you think of a traffic network, you can identify portions in which you have some free part and some congested part. And that portion becomes, let's say, a stretch to be modeled in this way. Well, it's a nice model in the sense that it's very simple. So you don't need a huge number of cells. You just have these two cells for any, let's say, portion. And well, it has anyway the property of being able to capture the relevant phenomena that you may have in traffic systems, such as shock waves, I mentioned before, but also rarefaction waves. So the waves that are generated when some congestion is very slowly typically resolved. And well, of course, there are other macroscopic models that you may be consider if you are interested to traffic control. There is the very well-known asymmetric cell transmission model, which was proposed by Professor Horowitz and co-workers. There are many different versions, multi-class versions of the CTM. And then there is the MetaNet model, which I believe Professor Papageorgiou has already introduced, which is a second order model. So a model which is capable of describing the evolution of the density in any cell in which you may subdivide a traffic system, but also the velocity of traffic. And this is something which incorporates the possibility of correctly describing the capacity drop effect that I mentioned before. And now let's say something about classical control. I focus, as I mentioned before, on freeway traffic control because it's something that I know better, to be honest. But this classical freeway traffic control can be subdivided in two parts. We have the so-called local strategies and the so-called coordinated control strategies. Typically, local strategies consider a very local, so typically small portion of the network, and of course in which you have some kind of actuation. And I say immediately what I mean with actuation in a classical traffic system control. In coordinated control strategy, you may have, let's say, the cooperation or a combination or coordination, to use the correct word, among different classical control systems. I mentioned which are the traffic control system and actuation mechanism for implementing this kind of control systems. The more classical one is the so-called ramp metering. So you have traffic lights on the on-ramps of the traffic system, and so you can meter and you can control the entrance of vehicles in the traffic system. Another very classical traffic control methodology is the use of variable speed limit. So you have limits, velocity limits on any lane typically of the traffic systems, and you may change the signals in order to slow down or let the traffic move at a certain speed, and this can create some regularization of the traffic itself. And finally, you may have dynamic routing, which means that, for instance, you can make some category of vehicles, for instance, trucks, to select an alternative direction, making the main traffic system, so the mainstream you are controlling, less congested. And these kind of techniques are typically also used, but in combination in a kind of integrated way in coordinated control strategies, which may be, as it is traditionally true, which may be based on optimization. And very often they also include some prediction capability, typically designing the control strategies using model predictive control. I want to give you some examples of these methodologies, and I will focus in particular on ramp metering. As I said, also considering, let's say, the topic of this summer school, I wanted to give an emphasis on optimization-based technique. So I start immediately considering model predictive control. What you see on the right part of the slide is a typical actuator, a traffic light, used to implement ramp metering. So you see you have a non-ramp and you have a red or green light, which regulates the vehicles flow entering the system. So if you look at this example, this is just an example of a controlled traffic system. We have the freeway system, we have some exogenous input, the mainstream and on-ramp flows, so the so-called demand, external demand. We have an output, which is the density in any part of the system. So I just put an underbar to indicate a vector. So if you decided to adopt a model based on cells, you will have a collection of the densities, in particular the densities in all the cells you are dealing with. You have also sensors, so you will measure the density through the sensor. They typically are, let's say, kind of magnetometers placed on the roads. And then you may have a reference for the density in any portion of the traffic system. You can compute an error, and you may have a model predictive based controller, which of course has to incorporate a predictor. And this predictor is typically a nominal model of the traffic system. So the models that we have seen up to now can be placed at this level in the traffic controller, in order to mimic as much as possible, let me say, with the approximation which are unavoidable in a model, the freeway traffic system we are controlling. Of course, you can immediately understand that the complexity of the model we decided to use as a predictor will have an impact also on the computation time and also on the accuracy of the computation, and also on, let me say, on the decision, for instance, to implement the MPC in a centralized way or in a decentralized or distributed way. So let me say that in general, when we use an MPC or optimization-based ramp metering controlling traffic system, we have some advantages considering the control objectives that I've already mentioned before. So the minimization of the total time spent in the system, the maximization of the total travel at a distance, the tracking of set point values, or any other kind of objectives, such as those related to sustainability, as we mentioned before. And you have the advantage of having some prediction incorporated in the system. You may have the advantage of having some optimality, or let's say suboptimality, but with acceptable difference with respect to the optimal solution. You may have the compliance with the constraints, which is something which comes, let's say, directly using MPC. But the drawbacks in a real system is that typically, in terms of computational load, the MPC algorithms are typically demanding, and they are difficult to be applied in a real system, especially if this is large scale. And so if you want to implement it in a centralized way and you have a complex and large traffic network, you may encounter some difficulties. So in particular, if you think or if you want to have an idea of what I did in the past with my colleagues to tackle this problem, so the complexity, the computational complexity, and the difficulties in implementing classical MPC approaches for traffic control, you can see what is presented in this slide, in which in particular I've tried to, let's say, provide a schematic of what can be done to make MPC-based ramp metering, in particular control schemes, actually usable in real system. Well, there are different ways to proceed. In particular, you could work on the optimization side. So what can be done is to make the optimization more efficient. For instance, I believe that Professor Papageorgiou presented some techniques that his group has developed very nicely in the last years to provide very efficient gradient computation. So this is something which can actually have an impact in the possibility of implementing the MPC. Another possibility is the reformulation of the model. So the idea is to approximate the model or to reformulate the model in order to make it more tractable, to make the optimization problem less complex. Another possibility, which is in particular the kind of things that I've done with my colleagues and my co-worker, is to decide to reduce the number of transmission of the measurements and reduce the number of times the control law is recomputed. So the idea is to control only when it is necessary, the traffic system, and to control only, and to transmit the state consequently only when it is necessary. But in addition to this, you can also do something else. Control only where it is actually necessary. So you may think of a very complex, large-scale network, and a very, let's say, basic idea is to control the network only where it is necessary, because some, let's say, difference with respect to the prescribed behavior can be detected in those areas, and only when it is actually necessary to recompute the action, the control action, and to transmit the measurements which are needed to compute the control action itself. And well, I've just listed exactly what I've just said to you, what we have done in particular in my group in the last years. We have started by reformulating the model, which is typically nonlinear, traffic model. You have seen the models I've presented before, the CTM in particular. I will focus on the CTM, but also if you think of the MetaNet. And the idea is, to eliminate those mean or mid that may appear in this kind of model functions, so mean functions and mid function that may appear in this kind of models, transforming this system into the so-called mixed logical dynamical form. And the prediction model in this way becomes more tractable. This is a possibility. Another possibility is to reduce the computational load and communication load of the MPC algorithms by making the MPC event triggered, so to control only and transmit only when it is actually needed. Another way to reduce again the numbers of recomputation of the optimal solution is to use an event-based MPC. So the idea of considering what is happening in terms of events in the traffic system, and so in case of accident, in case of, let's say, rapid increase of the traffic demand, in case of, let's say, capacity reduction because of some work in progress, then in that case, you may apply in some cases, pre-computed optimal control action, or the way a control action obtains solving an optimal control problem. And then, as I said before, a possibility is also that of designing a kind of decentralized or distributed MPC using the so-called cluster-based approach. So subdividing the network in a collection or a set of cells, creating clusters. I will give you some more details in a moment. And finally, there is an aspect which can be interesting also for people entering this field or interested to do research in this field. Consider that traffic systems are complex systems. They are nonlinear, they may be hybrid, they may be switched, they are highly connected, and they are very difficult to model, to be honest, even if, as we have said before, we have a good list of models to use, but there are some aspects which are difficult to capture. And well, this uncertainty, so this mismatch between the nominal model we can provide and the real system needed to be tackled in some way. Of course, you can use a robust MPC. This is an idea, but another idea, this is the idea that I followed in some papers, is to combine MPC with a robust control approach. And the robust control approach that I've used is sliding mode control, because it's one of my, let's say, main research topic. And well, I will tell you briefly something for any of this in a few moments. I will go on for 5 minutes more in this first part. And don't forget that it's also important to validate what you design in terms of control. In my experience, just to give you some elements, and maybe you may have a look at my papers, I had the fortune to be able to work with a nice group of people in a European project, ICON2 project. And in that case, a part of the project was devoted to develop a traffic showcase in Grenoble, in France. And in particular, we modeled and performed the control, designed the control for the so-called Rocade Sud, which is a portion of kind of south ring in the traffic system of the town. And of course, we have also done a lot of, let's say, virtual assessment or virtual validation of our algorithms using real data, which are available. There are many, let's say, databases. In particular, we have used many sets of data coming from the Netherlands. Okay, so I want to give you a very quick, let's say, mention of the topics that I've listed before. So this is the model that I start from to give you an idea of what transforming the classical CTM or a classical traffic model into a mixed logical dynamic form means. So this is the CTM. As I said, we have a cell which is characterized by let's say, an equation describing the evolution of the density in the cell, and we have some input flow, output flow. In this picture, I've also added some demand on the on-ramp. So I assume that I have an on-ramp and I have a flow of vehicles exiting from the on-ramp and asking to enter the cell. And we assume also to have some flow exiting the cell itself. Of course, if you think of these demands coming to the on-ramps, and if you think of a demand which is not indicated in the slide, but you may imagine it entering the mainstream, these are unknown quantities. They are disturbances in some sense, non-manipulable exogenous signals. And well, this is the state equation. And what you have to add is, of course, a model for the outflow from the off-ramps. And you have to describe how the flow entering the cell from the previous cell and from the on-ramps is handled by the model itself. And as I said before, you see that in this part of the equation that I don't want to comment too much, but you may have a look at them and read them with your time, so devote the time that is needed to understand these equations. There are some nonlinear operators, in particular this mid, which means select the quantities which stay in the middle. And well, an idea is to transform this kind of mid or mean and other equations. Sorry, I go back for a moment. There is also a mean, as you can see here, to determine, for instance, the demand, and also a mean function to determine the so-called supply that we have already mentioned. So one possibility is to transform any of the nonlinear operator that we mentioned before into this kind of equations where you have some new variables, which are logic variables, and some real auxiliary variables. So any of these operators are transformed so that the model becomes a new, let's say, becomes a new model in which the structure has changed. So we move from a nonlinear setting to a mixed integer linear structure. This, of course, is beneficial in the sense that when you solve the optimization problem, you can solve a mixed integer linear quadratic programming solvers, for instance, or a solver which is easier to use, and the problem itself becomes in some sense easier to solve. I give you an idea of the problem. So you may have let's say, the initial condition, of course, for the density and the length of the queues on the on-ramps. You may have the demand and the supply as known quantities, and what you have to determine is the so-called metering flow, so the flow exiting the on-ramps and being allowed to enter in a certain cell. And to do this, what is solved is a classical finite horizon optimal control problem. I show you the schematic, and if you agree, we can stop here for a moment. Is it correct? Kimia, it's almost time to stop, to make a break, or?
Well, you can decide as you wish. So we can either have a break right now, for I mean a quick break, or if you like, you can continue. So as you wish, we can do
as
it.
you prefer. If the student need a break, I stop. Otherwise, for me, I don't need a break, so I can also go on if you prefer, and maybe finish a bit before. Is it fine?
Yeah, sure, of course.
Okay, very good, very good. So if they agree, I hope that they not to be too. So for me, it's the break is not needed actually. Okay, so as I said, the solution of the problem is based on the classical approach that probably you know very well. So we measure the state and the estimate of the demand. We solve the finite horizon optimal control problem. We find the control over the horizon that we have decided to use, apply the first component of the control sequence that we determine, and go on again and repeat the procedure. The problem, of course, is different depending on the kind of cost function that we decide to use. I show you an example of what happens if we use a mixed logical dynamical predictor, and we want to solve one of the classical control problems for traffic system. For instance, if we use the so-called total time spent, and we want to minimize the total time spent by the vehicles in the traffic system, the cost function that we use may be a function depending on the density, depending on the length of the queues on the on-ramps to the traffic system, and the optimization problem that we have to solve in a finite horizon fashion is a mixed integer linear problem. If we want instead to minimize the so-called quadratic deviation of the state variables, which are, again, I repeated, the density and the length of the queues on the on-ramps, with respect to some pre-specified thresholds or set points, the problem becomes mixed integer quadratic, as I said before. And of course, there are other possibilities. In some of my papers, you may find the cost function that I've reported here. In this case, for instance, the idea was to minimize the cases in which the state variable exceed given thresholds that can be, let's say, set, considering the particular traffic system you're dealing with. Or another case is when you wanted to minimize the number of cells which are congested. So in some sense, reduce the diffusion of congestions in the traffic system. And in this case, anyway, you see that, again, the problem to solve is mixed integer linear in those two cases. So changing the model, so reformulating the model in mixed logical dynamical form is a way to reduce a bit the complexity of the problem, of the optimization problem to solve. But in any case, the problem is still complex. So the other possibility that I mentioned in the let's say, list that I showed to you before is to control the traffic system only when it is actually needed. And this means to adopt a kind of philosophy which is called event-triggered control approach. The schematic is the one reported in the slide. So we again consider to have the traffic system, we measure the state. So in case of the CTM, it can be the density in any cell and the length of the queues on the on-ramps. We have estimated the exogenous signal, the demand, which, as I said before, is something unknown. We solve the optimization problem. We find the control over the horizon that we have decided to adopt for the optimization, apply the control action in the sense said before, so the first component of the sequence, and then we check the triggering rule. The triggering rule is something which, for instance, may tell us if some change has occurred in the traffic system dynamics, in the traffic system evolution. If checking for instance, the density and checking the length of the queues on the on-ramps, we see that there is no major difference with respect to the previous time instant in which the optimization problem was solved. We can keep on using the same control sequence that we have computed before. So there is no need actually to solve again the optimization problem. And this is exactly the idea. So if the triggering rule is not satisfied, we can keep on using the same control sequence and maybe reaching the end of the vector. Imagine this sequence as a kind of vector. We use the first component, then the second component, and so forth, so on and so forth, until we reach the end. At that point, we have to solve again the optimization problem. Instead, if something new happens in the system, so for instance, an abrupt change of the demand, which means that the density in the system, not immediately, but rather quickly, typically undergoes a variation, well, you have to re-optimize. You have to solve again the optimization problem. And so in this case, you go back and repeat the procedure. So this is the idea. And well, the triggering rule is more or less the one that I said before. I just reported you an example of triggering rule. If you think of the MLD, so the mixed logical dynamical setting of the model, this variable, I didn't tell it before, but this is one of the logic variables we use to indicate if the system is congested or not. So if the system is congested, typically it becomes, this variable is 1, otherwise is 0. So what we do, for instance, to propose a triggering rule or to implement an event triggered control approach, we check this logic variable. So if it is not the logic variable, so the state, the mode of the system, congested or not, is not different from the one that we can retrieve from the prediction model. If the density we can measure on the system is not different from the one that we can retrieve from the prediction model, consider the measuring at the previous triggering instance, so the last measure that we collected. And if the length on the on-ramps is not so much different from the length that we can predict from the prediction model, considering the measurement that we transmitted at the previous triggering event, then we can keep on using, as I said before, the already computed control action. But if there is a different, and this different, it occurs in a good number, so in a certain number of cells in the traffic system, it's better to recompute the control action. So this is a quite typical triggering rule. So this is an example. So you see this is a system with 10 cells, 2 ramps, and in particular, this is the traffic evolution, in particular the density in the open loop case. And if you look at this picture and you see what happens when we apply an MPC approach, in particular to minimize the total time spent by the drivers, which means in particular to maximize the total throughput of the traffic system. This is something strictly connected. Well, you see that there is definitely a difference. So this was the open loop case, and this is the closed loop case. Of course, performing the ramp metering control means to observe an increment in the length of the queue. So I've also proposed here, reported here, the queue length for the 2 cells in which we have the on-ramps, which are the on-ramps, as I said, are the 2 points in which we actually perform the control, because we vary the flow exit in the on-ramps. Well, if you look at the result, you can see that the improvement of the total time spent is of the 7%. You may say that, well, this is not a very huge increment, but probably you have already heard in other lectures, I believe that Professor Papagiorgi already mentioned this to you. Typically in traffic control, the improvement that you may obtain is not so high. And when you find papers in which you see that the improvement in the total time spent is something like 68%, 70%, 50%, be careful. It's strange. It's very difficult that you managed with the ramp metering control in particular to obtain a so significant increment. But what is interesting is that this has been obtained using the event-triggered implementation of the MPC, which means that we have recomputed the control action, so we have solved the optimization problem only 28 times over the 180 time instant in which, let's say, the control time, so the time that we are used to verify or to perform this simulation, is subdivided. So we have a sampling time so that we have a 180 sampling instant, and we have computed the control only 28 times, not at any time instant. And you see that in spite of that, we have a very nice effect. Well, of course, using event-triggered control, this is something that I have to tell you to be, let's say, complete in my description. Event-triggered MPC control implies a number of issues which needed to be tackled from the theoretical point of view in particular. Well, the optimization problem, as I said, is solved whenever the triggering rule is verified. So when the triggering rule tells us that we have to resolve the optimization problem. And of course, this means that we are solving the MPC problem or the optimization problem in an asynchronous way. This means that very particular convergence and feasibility aspect need to be faced. The second aspect that I want to mention is a stability result. So when you work with traffic control system, it's every time an issue to consider which are the stability property that you may prove. And well, this is not so easy to discuss in general. If you look at my papers, very often we talk about input to state stability, input to state practical stability, input to state regional stability. So let me say that any time you deal with this kind of system, you have to be rather, let's say, careful in claiming, let's say, very, let's say, utopistic result, like global asymptotic uniform stability. Well, I'm always very, very surprised when I see something like that. But anyway, there are also other aspects to consider, in particular robustness aspects. And well, as I said before, very often there are a lot of effects, a lot of unmodeled effects, which, as I said, are not captured correctly by the model. And so it is important also to consider to use robust MPC algorithms or to couple MPC algorithms with some other robust techniques. Well, some replies to this question that I've, let's say, listed in this slide for your convenience may be found in the paper that I mentioned before. In particular, I suggest to have a look at this paper, which is not to refer to traffic system, but it's a theoretical paper on a synchronous networked MPC control with an inner loop in which a robust integral sliding mode control approach is included. So this may be useful in my opinion, and we have applied it in many cases with nice results. Okay, and well, I go very quickly now because I want to move to the second part of the lecture. So as I said, I still have to tell you a few words about the other approach that can be used. I summarize briefly. If you remember, I said that a possibility you have to make an optimization-based control approach applicable actually in a real traffic system. You have different possibilities. You may, let's say, reformulate the model in a way that the optimization problem becomes simpler. The second way is to control only when it is actually needed. So observe the system, the traffic system, and identify the time instant when you need to control, you need to solve the optimization problem, and the event-triggered approach is a good solution. The other point, the other possibility you have is to control the system only where it is actually needed. And a possibility, this possibility can be implemented subdividing the network. I just reported a stretch, but this can be extended to a more complex case in which you have actually a network with intersection and merge and diverge elements, and subdivide the network into clusters. What we did, for instance, in the past was to consider a portion of the freeway system and consider a collection of, say, contiguous clusters. And in this way, we created a kind of state vector for any cluster. And the idea of the cluster is that in any cluster, so the idea that you have to use to identify the cluster, to create the cluster, is that you have one single actuators. In the cluster itself, sorry. And in case of ramp metering, the single actuator means to have a single on-ramp. If you look at the literature, there are different solutions for cluster-based traffic control. Of course, one possibility is to use decentralized MPC. So for any cluster, you solve a control problem of optimization-based control problem as if that cluster were an isolated system, so no connection with the other cluster present in the traffic system itself. Another possibility is instead that of using distributed control. Well, there are different solutions. You may find really many solutions. If you want just to have an example, I don't think, I cannot claim that this is the best solution you may find, but well, a possible solution is the solution that you can find in the paper that I've indicated in the bottom, at the bottom of the slide. In this paper, we presented two different algorithms. The first one, algorithm one, is an algorithm which is called partially connected, non-iterative independent algorithm. So we have a kind of algorithm in which any local controller of any class, when I say local controller, I mean the local controller of a single cluster, solve its optimization problem, minimizing a local cost function, I've just indicated here, and this local cost function you see depends on the state of the cells in the cluster and depends on the input signal you may use to control the flow of vehicles exiting from the off-ramps and entering the mainstream. And this optimization problem, of course, produces the control sequence for the cluster itself. And then what is done to perform the actual control is to use this control sequence. In particular, you see the first sample of this control sequence plus a weighted sum. So you see there are some coefficient in front of the control variables here. So you may, let's say, weight the two components as you prefer. So use the result of the optimization for the cluster S, in particular, is the index of the cluster is S that you have solved, plus the component, plus the sequence which has been computed by the local controllers of the connected cluster. So you needed to receive the information about this control component computed. You see that I placed this arrow to indicate the fact that you receive these from the close cluster, the cluster which are close, the neighboring clusters. This is a possibility. And another possibility is instead to use a partially connected, non-iterative, cooperative algorithms, which means that any local controller solves its own optimization problem, minimizing a kind of partial non-local cost function, in the sense that the cost function is related to the cluster itself and to the neighboring clusters. And then the control of the cluster is performed using the optimal control sequence for the cluster and receiving the optimal control sequence from the neighboring cluster, and then weighting the two components in the way that you prefer to come up with a classical cooperative distributed MPC control law. And now I can conclude completely this first part, showing you the scheme that I mentioned before. So if you want to incorporate also a robust control algorithm together with MPC, a possibility is the one that, for instance, we have presented in the paper that you see here in the slide, at the bottom of the slide, in which we have decided to use sliding mode control at the level of let's say, the local loop for any cell of the system, and an MPC as a kind of high-level controller. So in this case, I just want to add some comments to the scheme, and then you may find the details in the paper. The MPC control is a supervisor in the sense that it is based on a prediction model of this traffic system, one of the models that we have mentioned before. It can be the MPC, the CTM, it can be the MetaNet. In this paper, we have used the MetaNet model in particular. And what is done is to produce a reference for the state of any cell of the system. A sliding variable is computed measuring and is computed locally at the level of, let's say, of the local controller of the cell, measuring the state of the cell itself, any cell itself. Let's look at cell number I for generality, measuring the state of any cell and comparing the state with the reference state provided by the high-level controller. This sliding variable is steered to 0 in a finite time by the sliding mode controller, and is steered to 0 in a finite time even if some meshed uncertainties affect the model of the system. So it means that what is done by the local controller is try to, let's say, reduce the mismatch between the prediction model used by the supervisor and the actual model of the cell. This is all I wanted to tell on the first part. And now let me just move to the second part. I go very quickly because I added some detail, but I think it's better to skip them, and you can find them in the paper. And let's move to the more modern, I call it like that, control approaches. As I said, the introduction of connected and automated vehicles in traffic system can be regarded as a kind of paradigm shift, in the sense that now, instead of having the need of using infrastructure-based control, think of what we have seen before. A ramp metering control uses a traffic light, which is an infrastructure-based actuator, to perform an action on the system. Now, the idea is, instead of using infrastructure-based devices and approaches to control the traffic system, the idea is to use the vehicles or some vehicles which are included in the traffic system itself. In particular, the idea is that of using the so-called connected and automated vehicle, the CAVs that I mentioned before, to create a kind of artificial moving bottlenecks. And this can be done in particular controlling the connected and automated vehicles individually, or by creating kinds of platoons or other kind of formations. For instance, in the paper that you see reported here, we decided to create a kind of formation which are not necessarily a platoon on a lane, but maybe a platoon plus another platoon attached or close to the first one in 2 lanes or in 3 lanes, so something more, let's say, articulated than a single platoon. And these platoons can be used as a kind of special actuators to control freeway traffic, exerting an action which is very often an action, let's say, oriented to slow down the traffic, making the vehicles arrive at lower speed towards the points in which some, let's say, physical bottlenecks are instead present. So we call these platoons moving bottlenecks to distinguish them from the physical bottleneck that you may have in a certain road, in a certain network. Of course, given a traffic system in which you have a kind of mixed traffic, when I say mixed traffic, I mean a traffic in which you have conventional vehicles and connected and automated vehicles, there are actually different possibilities to control the traffic system itself. And in particular, there are different possibilities if we want to use these connected vehicles as actuators, as I said before. One possibility is to control the connected and automated vehicles which are present in the traffic system as if they were a kind of macroscopic vehicular class. This is, for instance, something done in this paper that you see is co-authored also with Professor Kalle Johansson that you have seen this morning. And another possibility is, well, as I said, sorry, I want to add a few comments about this. The idea is in particular that of using a model in which, again, we consider some cells. So we subdivided the traffic system into cells. But for any cell, we have a description of the density of one class of vehicles, for instance, the classically human-driven vehicles. And another class, the density of another class, which is that of the connected and automated vehicles. And when we have the model describing the two classes, of course, we needed to keep into account the interference or the way in which the two classes behaves. And in particular, don't forget that in case we use the connected and automated vehicles as actuator, we have the possibility, or we assume to have the possibility, to control their velocity in order to create a regularizing effect on the overall traffic system. So this is a possibility. So control the connected and automated vehicle as a macroscopic vehicular class. This is something that can be obtained, for instance, using the approach that we have presented in the paper that I mentioned before. This is a classical density representation in which you see on this axis you have time, on this axis you have the number of cells, so you have space, and here what is represented using color, a color scale, is the density. So what happens if you look at this picture, it means that we have a congestion starting from this cell at a certain time instant and then propagating let's say backwards in the upstream cells, of course back in space and forward in time. And if we use the connected and automated vehicles, as I said before, modeled as if they were a particular class of vehicle, we can have, of course, a different control effect depending on the so-called penetration rate, so the fraction of connected and automated vehicle over the total of vehicles that are present on the traffic system. And you see that what we showed in the paper is that if we increase the penetration rate up to a certain extent, then, of course, the effects tend to become more or less constant after a certain level, but we have good effect. So you see that the density, the congestion tends to be alleviated, and the density tends to become lower with respect to the open loop case. Another possibility, so one possibility is the one that I've just mentioned, control the connected and automated vehicle, considering then a single class. And the vehicles which are driven classically by humans are another class. Another possibility is to control the connected and automated vehicle individually. We can assume to have a controller for any vehicle. This is a possibility, of course. This is a possibility which is very easy to implement, technologically speaking, but the control is not so easy to design, in the sense that we have to reach a kind of balance between the selfish behavior, which is typically caused by this kind of setting, with the social optimum that we want to reach. An idea is, for instance, to use some kind of game theory-based approach in which the vehicles are agents, individual agents, which tends to play a game against. So there is no cooperation, but maybe we want to realize a kind of cooperative game, even if we have a setting which is typically of a game which is not cooperative at all. Of course, the cooperation can be enforced, and can be enforced, let's say, also using the connectivity that we have, the possibility of exchanging messages among the vehicles, which are the cars, our actuators in particular. Another possibility is, as I said before, to create formations, such as platoons. Again, in this case, you may decide to control the platoons in a centralized way, so assume to have a kind of how can I say, single centralized controller having information on the entire network and on all the platoons which are moving on the network. And this can be, let's say, computationally demanding and also demanding in terms of measurement transmissions. Another possibility is to use local controllers for any platoon. Again, the game theory based approach that I mentioned before can be transferred to this case, and some form of cooperation exploiting the communication capability that the vehicles may have must be, let's say, enforced. And this is exactly, the arrows indicate what I just said. Well, a comment on the model. Depending on the approach that you decided to adopt, you remember what I said before, curves controlled as a macroscopic vehicular class, curves controlled individually, curves controlled to create platoons or other formation. Well, depending on the approach that one decides to use, you need to formulate a different model. If you use if you decided to control the curves as a macroscopic vehicular class, varying, for instance, the headways of this class or the velocities of these vehicles as a class, I repeat, not individually, you need anyway to use a single scale model. That is a model in which both the class of human-driven vehicles and the class of connected and automated vehicles are depicted, are represented at a macroscopic level. But if you decided the other two approaches, so if you want to control the connected and automated vehicles individually, or the connected and automated vehicle in order to create formation, the modeling approach must be completely different. It must be multi-scale, because at the same time, you have to describe the evolution of the connected and automated vehicles, which are, let's say, individual vehicles. They are kind of single agents. They are microscopic vehicles, which are immersed in a macroscopic flow. So you have a two scale at the same time, and they coexist, and they must be described mathematically at the same time and in the same model, incorporated in the same model. And this picture wants to describe, let's say, in a pictorial way what I've just told you. So the idea is that now, if we want to design a control system for a traffic system, using this new vision, this new idea that of controlling the system using this connected and automated vehicle, which are themselves part of the system, we need a completely different modeling approach. So we need, in particular, a model which includes at the same time, in the same formulation, the macroscopic traffic to describe, as I said, the road traffic, the entire traffic system. We need a microscopic level to describe the single connected and automated vehicle. And then if we wanted to enforce the creation of platoons, formations, we need also a mesoscopic level where car following effects are visible, are described. And well, this is the novelty in some sense. And what I'm going to tell you in the last part of the lecture is something about what we have done using these different approaches, and in particular using multi-scale models. I start with the CTM. The CTM is a model that we have already considered before, cell transmission model, so the traffic system is subdivided into cells. And now the difference that we have with respect to the first part of the lecture is that we assume to have, apart from the macroscopic traffic, also some connected and automated vehicles. They may be individual or they may be platoons. I assume, for instance, that they are platoons, but I repeat, the formulation remains similar. You have only to consider some different effect you may have in case of single vehicle or a formation of vehicles. There is a different reduction of the capacity which is performed by the two situations. So as I said, a possibility is to incorporate the presence of platoons, which are very often called moving bottlenecks, in the traffic system. And in case of the CTM, you remember that the CTM is a model in which for any cell we have a first order equation describing the density. The presence of platoons can be described introducing this variable ho with j, which describes the so-called occupancy of the platoon, and the index indicated the index of the platoon itself, so platoon number 1, 2, 3, up to a certain number, capital J. And this delta is a variable which indicates the presence of the platoon in a cell. And so this is, say, the way, adding this term to the classical CTM is the way that we adopted, in some papers at least, to modify the basic CTM to incorporate the presence of the platoon. Of course, the presence of the platoon has an effect on the so-called free flow speed. The free flow speed is typically the speed associated with a certain cell, which describes the velocity of the macroscopic flow in case of no congestion, so in case of the traffic is not congested. And well, when we have this moving bottleneck, the classical free velocity of the macroscopic traffic may be reduced, in the sense that the platoon exerts an action, as we have said, it reduces the capacity of the, for instance, if you look at of the cell itself. So if you look at this picture, you can imagine to have, let's say, 2 or 3 lanes, and one lane becomes partially occupied by the platoon itself. So typically the velocity in case of presence of the platoon in a certain cell is a function of the velocity of the platoon itself. And well, this is a way to describe the platoon. This is the way that we have adopted in the paper that I've already mentioned before. I reported here the paper again. For instance, in that case, we designed a kind of centralized control in which we use as a control variable the speed of the platoons which are present in the traffic system. So what we do in practice is to solve an optimization problem in which we find the optimal control sequence, and in particular the control variable that we use is the speed of the platoons which are present in the traffic system, and the optimal control sequence, so the optimal velocities that any platoon in the traffic system has to maintain, is computed solving an optimization problem, an MPC control problem to be precise, in which we go to minimize the so-called total travel time, as you have seen before. We also minimize the displacement of the difference between the density at the bottleneck location with respect to the so-called critical density. Probably you have already seen that this is what is normally done, considering that at the critical density, the capacity of the road, so the flow that a certain cell can, let's say, can accommodate is the maximum flow. So it's quite typical to introduce a term to maintain the density as close as possible to the critical density, avoiding anyway to enter in the congestion phase possibly. And another possibility is another term that was present in the cost function is a term which is intended to maximize the discharge flow from the bottleneck, which means that when you have a bottleneck, you wanted to reduce the capacity drop after the bottleneck itself. And so, well, apart from the cost function, which is an example, so you may also use platoons of connected vehicle with different cost functions. But just to give you an idea of the possible result, I use this cost function, and I propose to you some simulation results which were obtained using a road, a piece of just a stretch of road in which we have 16 cells, and each cell is has a length of 500 meters. And what is done is we create a kind of temporary physical bottleneck, so something which is not moving, differently from the platoons, which are, as I said before, moving bottlenecks. And this temporary physical bottleneck is placed in a certain cell. It's cell number 13. I tell you the number because in the picture it's useful to remember in which position the physical bottleneck is located. This physical bottleneck has an effect in terms of reduction of the capacity. And this physical bottleneck is left present in the system until a certain simulation time, until this point in time, and then the total capacity is restored, so the physical bottleneck is removed. Just to give a real world example similar to this scenario is when you have an accident. The accident creates a loss of capacity, and then after a certain time the accident is, let's say, solved, and the total capacity of the infrastructure is restored. Well, what is done in this simulation is to observe 2 hours of simulation and assume that several connected and automated vehicles entering the stretch, creating 13 platoons of 2 vehicles each. And well, this is the result. Let me show you the result if I want to go on. This is the result you may obtain with the CTM, so simulating the system that I've just described with the cell transmission model without the capacity drop modification that I mentioned in the first part of the lecture. I show you this picture because you will see that it is useful. If you look at this picture, probably you understand that the CTM without the capacity drop modification is not very realistic, because look at what happens. So you have a physical bottleneck at cell number 13. Some congestion is created in the cell before the 13th one, so in the 12th cell, and this propagates only in time. No, let's say, backward propagation of the shock waves, not very realistic. If I use the CTM with the capacity drop effect, look at the situation. This is more realistic. I have the physical bottleneck, I have the congestion. It is, of course, majorly present in the cell before the one in which I have the congestion, I have the bottleneck, but the congestion propagates also backwards in the upstream cells as it is natural. So this is the realistic situation. So these 2 cases are those in the open loop case. I adopt the CTM with the capacity drop, and I use as a control, the control that I've just described to you, so obtain solving the optimization problem based on the cost function seen before, and using the 13 platoons of connected and automated vehicles that I have mentioned before. So you see that using 13 platoons, which is not a huge number of, and any platoon is just built with 2 vehicles. So it's a, let's say, minor kind of control action. We can obtain an effect in terms of control, which is rather similar to the case in which we don't have a capacity drop. This is why I've reported this picture. And this is exactly what we want to obtain with the control. So reduce the capacity drop effect, reduce the back propagation of the congestion, so reduce the shock waves which affect the traffic system. So you see that the idea of using connected and automated vehicle can be effective. And well, congestion is mitigated, as I said, and this, of course, has a beneficial in terms of travel times reduction, emission reduction. Don't forget that when we reduce the congestion, we also have a beneficial effect on emissions, fuel consumption, and so on and so forth. Well, this was an example. So I've just discussed an example in which I showed you how to use the CTM with a slight modification in order to incorporate connected and automated vehicles. Another, let's say, more complex way to deal with the connected and automated vehicles is that of coupling a continuous model, so a PDE-based model, with a model describing the dynamics of the individual cars, the individual connected and automated vehicles. They are described by means of ODE. So what at the end we proposed is a PDE ODE model for the multi-scale description of traffic system. And I want briefly to give you an idea of what I mean with this kind of title. Well, this is a model which was actually proposed by my collaborators, by the people, by two nice person with whom I like so much to work, which are Maria Laura Dalle Monache and Paola Goatin. Well, they proposed this model in which there was a PD model, probably you remember the LWR model that we have seen at the beginning of my talk, which described the macroscopic traffic flow. This is a classical conservation equation. And then we have a constraints on the flow, which describes the moving bottleneck position, which means that it's a kind of constraints on the capacity. So there is a reduction of the capacity due to the pointwise presence of a connected and automated vehicles. And the evolution in time, so the motion of the moving bottleneck, I use this moving bottleneck term as a synonymous of connected and automated vehicle. For us, the connected and automated vehicles are in practice moving bottlenecks in the traffic system. So the evolution in time, in particular the motion, so the space traveled by the connected and automated vehicle, is described by the ODE that you see here. So this was a model which was already present in the literature when I decided to face the problem using this approach. So I found this model and I decided to use it. And so I started to collaborate with Maria Laura, with Paola. In particular with Paola, we immediately wrote together a paper in which we solved a control problem using this model. But apart from that, and as I added this commentary, particularly in the paper that you have here for your reference, we solved an MBC problem to reduce the overall travel time by varying the overall, when I say overall, I mean of the entire traffic system, by varying the velocity of the connected and automated vehicle. So we act on the overall traffic system by varying the velocity of the moving bottleneck. But apart from that, we observed that the model, which was already there, was not enough to describe the formation and in particular the platoons of connected and automated vehicles. So we decided to work on the model again. And together with Paola Goatin and my former PhD student, Giulia Piacentini, we further modified the model in order to incorporate the presence of platoons. If you think of a platoon moving along a traffic system, this can be a piece of road, a stretch of road, you have that the platoon is characterized by the position and velocity of the front end and by the position and velocity of the back end. And then, of course, you can assume to have some low-level control of the platoon itself to have a constant or, let's say, but what is more constant in time typically. So what is typically done to have an headway, which depends, which is correct considering the velocity of the following vehicle. So the headway between two vehicles typically depends on the velocity of the vehicle, which is the follower. Well, apart from the low-level control, which at this, let's say, moment, so for this presentation is not so important, we assume that a low-level control to maintain the platoon is present, it is interesting to have a look at the model. The model is, again, a coupled PDE-ODE model in the sense that the macroscopic traffic flow is described by the LWR model as before with the conservation equation, the traffic fundamental diagram, and initial distribution of the densities all along the road. And then the front end and the back end of the platoons are described by means of two ODEs now. So you see that we have this model in which we have described explicitly the velocity of the front end and the back end, so the upstream and the downstream point. I go back to the model. So this is the downstream point and this is the upstream point of the platoon. They are described, the velocity of those two points of the platoons are described by means of these two ODEs. And if you compute the difference between the two velocity and you integrate this quantity, you can get the length of the platoon. This is positive, let me say, for the control, because we can use the velocity of the platoon itself, assuming that, I mean, there is a low-level control maintaining the velocities of all the vehicles of the platoon at a given velocity, but we can also use the length of the platoon. So we have more flexibility in the control. So this is the idea. Well, this new model was presented in the paper that you see here reported, and well, it has a feature which is interesting to observe, the fact that now the fundamental diagram is discontinuous. So when you have that the platoon is present or enters a cell, there is a kind of jump, because the reduction of the capacity, so the platoon, as we have said before, creates a kind of a reduction of the capacity, and this reduction of the capacity is moving along the road and depends on the velocity of the platoon itself. So what happens is that if you think of the traffic flow as a continuous system, so think of the conservation equation which describes the density in time and space, you have an effect on the density which is mainly due to the fact that there is a motion of this platoon along the road and a reduction, a kind of jump sometimes when the platoon enters in the cell, you have a jump of the fundamental diagram. This is due to this jump in the incoming demand and the jump, corresponding jump in the supply that a cell can offer when the platoon is present. So just to give you an idea, you see that if the platoon is not in a certain position, so if the point in space is not inside the platoon, we have the classical fundamental diagram. But when the point in space you're dealing with is inside the platoon, so to say it differently, if the platoon is in the cell, and in particular in the point, if we look at the system as a continuous system, in the point you are looking at, you have a reduced traffic fundamental diagram due to the corresponding reduction of demand and supply. This fact has to be dealt with, and well, this was the critical technical aspect to deal with. We had to invent, let's say, a way to deal with this jump in the traffic fundamental diagram. And well, I don't want to go too much into the details. I want to leave some time for real question, but consider that in particular, just to give you an example, if you look at the front end case, what we had to do is to find a way to be explicit on the fact that when we have this front here, we have a kind of jump in the density. And what we have done in particular, just to give you a kind of hint, is to approximate the density at the left part of the jump front of the platoon front, let me call it like that, with the density in the cell before the cell we are dealing with, and the density after the front with the density in the cell which the platoon has to enter after some time. And considering this approximation, we can formulate a Riemann problem. And of course, this is a very classical mathematical problem. And what you need to do is simply to apply or to design a kind of numerical approach, numerical method to deal with these kind of shocks, which are called non-classical shocks. for, in particular, for couple PD ODE pronouns. Well, we did it in this paper. If you're interested to the details, I don't want to enter too much into them. But this works pretty well. So I don't know if you can interpret these pictures. If you look here, you have time, so they are different, let's say, snapshots. We have space and we have density. And the 2 points are the 2 red circles, small red circles are the front end and back end of the platoon. So the platoon starts here, and moving the platoon in space, you see that the density undergoes a modification, and some shock waves it created behind the platoon itself, a rarefaction wave it created in front of the platoon, or close to the platoon, to say it differently. And these kind of waves are propagated along the traffic network. So I'm trying to describe very, say, in a very simple way, these phenomena, which are not simple at all, but it's nice to know that this model works pretty well. Well, this model was used also to solve a control problem. And this is what you can find in this other paper that I've indicated for your convenience. So the idea, as I mentioned before, is to use both the speed and the length of the platoon. And well, this is done. In particular, in this paper, we have also used as a cost function, a function which describes the so-called total fuel consumption of the traffic system as a function in particular. This total fuel consumption is written in terms of the density. And well, this is the optimization problem that we have solved. You know that there is a constraint for the length of the platoon, there is a constraint for the velocity of the downstream part of the platoon, there is a constraint on the difference between the upstream and downstream velocity, so the velocity of the downstream and the upstream point of the platoon. But the problem was solved, and well, this is just the behavior of the total fuel consumption model, but I want to show you instead the result in simulation. So again, we have a case in which we have 200 cells, so a road, a fixed bottleneck at the end of the road, and a certain arriving demand, and we have in particular this arriving demand, which is rather high for half of the simulation, and then it tends to become zero, as you can see here. And the output of the road is reduced by half by this kind of fixed bottleneck that we have. And well, this is the case in which we don't have the control, so open loop case. This is the density increment. Yellow means high density, so this is the congestion produced by the physical bottleneck, which is placed at the 5th kilometer, so the last at the end of this road stretch. And this is the effect that we obtain with the platoon. So the 2 lines that you see are the upstream and downstream and upstream part of the platoon. So you see that the length is varying, probably you can observe it. And the density here is reduced, so the congestion is reduced. And what is seen here is that the platoon creates a kind of controlled lower congestion behind the platoon itself, so it tends to slow down the traffic to avoid that the vehicles are, let's say, gathered or together against the physical bottleneck and create the huge congestion that you see here. This is the variation of the front and the back end speed of the 2 vehicles. And well, in the paper, you can see the example for the cost function written in terms of fuel consumption. And what can be observed, for instance, in the simulation that I've reported here, just as an example, that there is an actual saving in terms of consumption. In particular, a saving of 726 liters, considering that the simulation we consider was on a small road stretch, 50 kilometers are not so much, and only for 1 hour of simulation. So the effect is relevant. Well, I'm concluding. well, I skip here. Just a mention to the fact that if you are interested, we also published a MetaNet version of the model for incorporating platoons of connected and automated vehicles. I've just prepared a slide on this that you may check if you're interested. Even in case of the MetaNet, we can obtain good result with the control. And well, of course, the model is more complex in the sense that we have both the dynamics of the density and of the velocity explicitly reported in the model, included in the model. But again, the model is a new version of the MetaNet in the sense that it is, as it is written in the title, a macro version, so multi-scale MetaNet model, let's call it like that. And this is all. These are my conclusion. In this letter, we have seen something related to the classical approaches with some elements, in my opinion, of originality, in the sense the event-triggered approach, the cluster-based approaches can be interesting for people, for those who like to enter, let's say, the field of traffic control. Then we have moved the attention to multi-scale models, in particular those capturing the presence of connected and automated vehicle in the traffic system itself. And I've mentioned the CTM with connected and automated vehicle. I've mentioned the so-called couple PD ODS models. And I've also briefly mentioned the MetaNet with connected and automated vehicles. We have seen with some examples, of course, you may find other examples in the paper, that the use of connected and automated vehicle may be effective. Let me say that I define the effect of connected and automated vehicle promising, in the sense that, of course, we have still to study, we have still to learn how to make the most of this possible way to control traffic system. And I conclude showing you some papers that can be useful, some references that I've used in particular to prepare this talk. There is a book that probably you have already seen, which I've written together with Simona Saccone and Silvia Siri recently, a couple of years ago, so free traffic modeling and control. The classical part is completely included in the book. Then there are some other papers. This is more related to sustainability, so I remember the comments at the beginning of the lecture. And it may be useful if you are working with sustainable mobility. This is the paper dealing with the model, variable length cell transmission model that I mentioned before, very convenient for traffic control. There are other papers you see here that may be useful for you that I've used in particular for the presentation of today. I want to mention this last paper, which was very recently published. It's already available online. And it's a survey paper. So it's a survey paper in which, in particular, the more classical aspects that I mentioned in this talk, but also many others are reviewed. And there are many references. So I think that for those of you who may decide to work, or some of you who are already working in traffic control, this can be a useful reference. You find a kind of a survey of the literature, some, let's say, comments on the major trends that have been, let's say, visible and relevant in the last decade. And well, this is actually all for me. Thank you so much for your attention. I hope that you have been able to learn something also from my talk. Thank you so much.
Thank you, Professor Ferrara. That was an interesting talk. It's always interesting to see that how we can really combine different things like the micro level and macro level together, and then maybe derive some new control method or actuator somehow. Yes. I would like to ask if someone has a question so we can discuss here. Maybe you can write in chat or unmute yourself and ask your question.
Or also send me questions in the future via email. So your questions are very welcome, even let's say offline. I know that typically asking questions online may be, let's say, a bit difficult, but if you reviewing the slides, find any points in which you need some additional information or you have some doubts, just write me. I can also provide some paper or some support material which can be useful for you.
That's quite interesting. Actually, I have a question about the part of the lecture that you were talking about the clustering of the different cells. So is it possible really when we have like a freeway that the cells have different fundamental characteristics, like we have the cell that the number of lanes are changing and then we have multiple on-ramp and off-ramp really frequently in the freeway?
Yes, you're right. This is a point which can be used also to clusterize the system. So if you remember, I mentioned that we decided to consider a cluster, a set of cells in which we have a single actuator. So for instance, a single on-ramp, if you use a ramp meter, and it can be a single variable speed limit, let's say, actuator if we use this other technique to control the mainstream traffic. There are, of course, other possibilities. So, you know, clustering system is a kind of, let's say, research trend itself or research field itself. So you can also decide to create a cluster if the cells which are in the cluster have homogeneous features. For instance, they have the same number of cells, or they are fundamental diagrams which are not too much different one from the other. So you can, let's say, set a kind of limit on the difference between two fundamental diagrams to consider that the two cells with those diagrams are part of the same cluster. This is a possibility. If you look at a real traffic system, so you think of, say, you have data on the morphological aspect of the system, you can also look at a morphological aspect like, let's say, the slope of the road, for instance, or maybe you can also decide to include a single physical bottleneck. I give you an example. A physical bottleneck in a real system may be, as you said before, the fact of having maybe 3 lanes before and then 2 lanes from a certain point onwards. Or it may be the presence of a bridge. So for instance, when you have a road on the, let's say, a classical road, and then the road goes on a bridge, there is typically an effect which is similar to that you may observe when you have a physical bottleneck. So also the idea, so how to cluster a traffic system is a kind of, let's say, research topic by itself. And let me say that this is an aspect upon which I would like to work. I've not done much, to be honest. I have some ideas in mind, but there is still a space, in my opinion, for research. You know that there are techniques which are useful to cluster nonlinear system in general. So if you have networks, complex network, and they are, let's say, complex, they are nonlinear, as I said, but in particular the network, there are ways to cluster them using some techniques which may be, let's say, related to the reduction of the complexity of the models itself. But how to extend those techniques into traffic system is something which could be a good topic to investigate, and I would be very interested to discuss this topic with any of you who may be interested in having a look at this problem, which is an interesting problem.
Yeah, that's true. Yep. I think we can also, I mean, the clustering could also be used maybe in other form of the traffic problems also. Maybe
Yes.
a little bit when you have the only the microscopic traffic. You can also use the clustering between the vehicles, like, okay, when you want to define the different platoons, then decide where to form the platoon and what vehicles to cluster together as a platoon. I don't know, maybe it would be a lot of ideas.
Yes.
Of that.
This is a very nice topic. I would be very happy to further discuss this. This is something also related to controllability of the system. So I like this topic because I've already I've thought about it. And for instance, as I said, it's not easy a priori to understanding how many platoons you may create. And when it is not needed to have so many platoons. So it may happen that at a certain moment you have a certain number of platoons, and then considering the condition of the system, you may decide to merge some of them to reduce the numbers. So again, what you said, clustering in this sense could be an action which the control system itself should be able to implement in an automatic way. And this is again the result of an optimization procedure. So, you know, this summer school related to optimization offers different, let's say, possibilities to people or to students or to researchers who would like to tackle the problem of traffic control with connected and automated vehicles. Because actually different optimization problem can be formulated, not only those that I mentioned in my talk, but also others which are related to aspects like clustering, for instance, and also to the volume, let me say, to the number of moving actuators that you need to realize a good control of the system itself. It's a very interesting topic. Very good point. Very good point, Kinya. Thank you for your comments. I like it very much.
Thank you for your talk. Okay, I think